All right, in the previous unit, we looked at the first fundamental theorem of calculus. Now, there's actually some argument over which one is the first one and which one is the second one. So it really doesn't matter. But the way that our text and our curriculum is going to define this is this one is going to be the second fundamental theorem of calculus, which you will often hear me refer to as FTC 2. Okay. So the second fundamental theorem of calculus says this. This really gets at the relationship between a derivative and an integral as inverses of each other. So if f is continuous on an open interval I and containing a, then for every x in the interval, the derivative of the integral from a to u of f of t dt is going to be equal to f of u times u prime, the derivative of u. Now, this is kind of hard to follow what we're looking at. So a couple of things to remember here, and we're going to kind of do sort of a casual proof of what it is that we are looking at. So a couple of notations here to think about is first, remember that u is an algebraic expression. So u typically contains a variable of some sort, okay? A is a constant. So A is going to be some real number, okay? Now, if we kind of walk through this proof, I think it's a little bit easier to see what it is that we are getting here. Essentially, look what happens. When you take the derivative of an integral, they undo each other and you're just left with the function. Now, there's an element of the chain rule in here, which matters. And we'll get to why in just a second. So for this proof, let's let capital F of x be an antiderivative of f of x, little f of x. That's notation that we have seen before. Okay, so that was no problem. So what we want to say then when we look at this is let's start with what we want. We want the derivative with respect to x of the integral from a to u of f of t dt. We've already kind of mentioned this idea of using t as a dummy variable. Since u is in terms of x, that's where the x's are going. We don't want to confuse that with what's inside the function f. So order of operations, let's work from the inside out. So what we would get, we haven't done the derivative yet, but inside here, the antiderivative of f of t is going to be capital F of t. And we want to evaluate that from a to u. Okay, well, that uses the first fundamental theorem. So we have the derivative with respect to x of f of u minus f of a. So there's our derivative. Now, we can take the derivative of each of those terms. Now, when we do that, remember what's important here is that f of a, since a is a constant, f of a is also going to be a constant. That's important when we go to take our derivative, right? So if we take the derivative of capital F of u, since capital F is an antiderivative of little f, then that means that the derivative of capital F is going to be little f. Okay, so when we take the derivative of capital F of u, that is going to be f of u, but because of the chain rule, we have to multiply this times u prime. The derivative of f of a is going to be 0 because that's what happens when we take the derivative of a constant. So here is what we get. Ultimately, we get f of whatever u is times u prime. That's what happens when we take this derivative. So we may still not really be sure what's going on here, but notice that we started with f of t dt. We ended up with f of u times whatever the derivative of u is. So the function that's inside the integral didn't change. The derivative canceled out the integral on the outside, but the function itself stayed the same. The input changed, but the function stayed the same. Again, really important here is that the bottom limit is a constant. It doesn't work if it's a variable. So we might have to flip our integral, or we might have to split it apart. So here's a few examples. We want the derivative with respect to x of the integral from -2 to x of t cubed minus 1. So in this case, u is just equal to x. So that means that du, or u prime, is just equal to 1. So when we take this derivative, the bottom number doesn't matter. We just saw that up here, that no matter what this bottom number a is, the derivative of that constant is going to be 0. That's why the number itself is irrelevant. When we take this derivative, we're going to get the square root of, instead of t, we're going to replace the t's with x, because that's what u is. So this is going to be x cubed minus 1 times the derivative of x, which is just 1. So that's the answer. Done. Okay, number 2, a little bit different. On number 2, u here is x cubed. So that means that u prime is going to be equal to 3x squared. So we will have to do a little bit of multiplying there. So what we want to do, the constant on the bottom doesn't matter. The answer is going to be the cosine of, replace the t's with u. Well, u is x cubed. So that's going to be x cubed squared plus 1. And then we have to multiply by 3x squared. Now, again, what is all of this? This right here is f of u, and this is u prime right here. That's what we're ending up with. So the answer, when we simplify this down, is going to be the cosine of x to the 6 plus 1, and I think it's probably nicer to write the 3x squared in the front. So that is what we get when we take the derivative of this integral. Now, on the next page, we're going to look at this in a little bit different context, but I do just want to mention, if we had an integral, like I said, that had two variables, let's say -x to +x of f of t dt, we can't do this theorem if it's got variables in both spots. You can pick any constant you want, because remember, it doesn't matter what it is, it ends up going away anyways. So I always pick 0. We would want to rewrite this as the integral from -x to 0 of f of t dt plus the integral from 0 to x of f of t dt. Now, the second one is fine. The constant is on the bottom. The first one is not fine because the variable is on the bottom. So we would have to reverse this integral, which makes it now negative, but the rest can stay exactly the same. And so that's how we would set this one up. If we wanted the derivative of this, like the other problems, then we would just want the derivative of all of this, and we would follow the same rules from there. But it has to be a constant on the bottom of the integral. That's the most important rule. All right. So on the next page, this is that idea of a function defined as an integral. So we have this graph. The function f is defined on the closed interval from -3 to 10 and is given by the graph above. Let g be the function defined by g of x is equal to the integral from 3 to x of f of t dt. Now, for a, this is what we've been doing before. So find g of 10, put in 10 for x, find g of -3, put in -3 for x. Go ahead and pause the video and try this one yourself. See if we remember how to do this, and I'll come back with the answers in 3 seconds. Alrighty, here are the answers you should get. We've got half of a circle plus a triangle for the first integral. The second integral turns out backwards, so we have to flip the order and make the integral negative. And don't forget that this area here from -3 to 0, that area is considered negative area. So this down here is going to be negative, and then we have this whole triangle here to get to +3. That has positive area. So that's why we end up doing -1/2 plus +15/2, and then use the negative at the end. Okay, here's the next question. We want to find g prime of -1 and g double prime of -1. Well, we're going to start, we'll go back to the graph here in just a second. But remember, this is G. So we need to start by finding G prime and G double prime. And let's find them in just the general terms for now. So G prime of X, based on what we just learned about FTC2, G prime of X is going to be the derivative with respect to X of the integral from 3 to X of f of t dt. You don't have to necessarily write this out, but for your notes, it's a good reminder of what we're doing. When we take that derivative, this is just going to be f of X times the derivative of X, which is just 1. So that's it. So G prime of X is just equal to f of X. And now that we know that, that tells us that G double prime of X is going to be the derivative of f of X, which is just going to be f prime of X. Okay. So if I want to know now the value of G prime of -1, I know that that's going to be the same as f of -1. Well, if we go to our graph, f of -1 looks like that is at +1. It's just the y value because the graph that we have here, this graph is f of X. Okay, so now if we want G double prime of 1, we want f prime of 1, which means we want the slope at x equals -1. And in this case, the slope is also +1. So G double prime of -1 equals f prime of -1, which is equal to 1. Now you'll notice making this connection between G and F, I'm being very deliberate about that. That's really, really, really important. You cannot talk about F without connecting to what's happening with the function G. That will never receive full credit if you just make statements without showing where that connection comes from. And so that's the answer there. Now we want to know, determine any x values where G of X has a relative minimum or maximum and give a reason for your answer. So this is going back to a lot of our derivative stuff from before. To find relative mins or maxes, what do we need to know? We need to know where G prime of X equals 0. Well, we know that G prime is equal to f of X. So our critical numbers are going to be wherever f of X is equal to 0. So that's going to be at -2, +3, +7. -2, 3, and 7. Since this is relative maxes and mins, that means we can just use the first derivative test, hopefully. And so we want to look at -2, +3, and +7. And we want to know, where does the derivative change from positive to negative or negative to positive, depending. So if we look at this here, to the left of -2, f of t is negative, which means G prime is negative. From -2 to 3, the graph is positive. It's above the x-axis. From 3 to 7, it is also positive. And after 7, it is also positive. So the only place it changes signs is at -2. And since it changes from negative to positive, we know that we have a relative minimum at x equals -2, since, now again, we always need to make the connection. So we'll say since G prime of X equals f of X changes from negative to positive. I cannot say it enough. Making that connection in your explanation is always critical. No pun intended. Last one, for -3 to 10, find all values for x where the graph of G of X has a point of inflection, and explain your reasoning. Now, this is where we have to go back to what have we been given. Could we find G double prime of X? We can, but G double prime of X, remember we said is equal to F prime of X. We do not have the graph of F prime. We only have the graph of F. So our answers need to be in terms of what F is doing. When we are looking at F, which is also G prime of X, that's what this graph also represents based on this scenario, then the question is, where do we change from increasing to decreasing or vice versa? In other words, what are the relative extrema of G prime? Okay, so we have relative extrema, and we can't include the endpoints because it was an open interval, at X equals 1, at X equals 3, at X equals 7, and right here at X equals 5, because that's a relative maximum. We're looking for maxes and mins along the graph. So the answers would be X equals, I already forgot what they were. Let's see, 1, 3, 5, and 7. 1, 3, 5, and 7. Since these are the locations, locations of relative extrema of G prime equals F of X. Always connect. And that's all you have to say. You could say it's where G prime equals F of X changes from increasing to decreasing or vice versa, but this is a little bit more concise of a way to say it. So this is how our integrals and our derivative worlds are kind of colliding. And this is how we can use these integral accumulation functions to interpret a little bit more about what is happening. We're going to go a lot deeper to this in this unit, and that is where we will stop for today.